let me say in Russian, спасибо за приглашение. К сожалению, после 50, почти 50 лет за границей мне дать настоящий такой scientific talk по-русски было бы, наверное, немножко непросто. Так что, so I'm converting to English. Here is my epigraph. The only difference between a probabilistic classical world and the equations of the quantum world is that somehow or other it appears that if the probabilities would have to go negative. Okay, that's the fundamental problem. I don't know the answer to it, but if I try my best to make the equations look as near as possible to what would be imitable by a classical probabilistic computer, I get into trouble. So this is the famous Richard Feynman, who likes to sort of speak aloud, think aloud, for which I'm very grateful to him. So I highlighted negative probabilities. I also highlighted simulation physics with computers. That's where his interest to this topic came, and same with me. So last 20 years of my career, I worked at Microsoft Research. In the last about 4 years, I became interested in quantum computing. And so my interest comes from there. Okay, introduction. So this talk is based on a paper with Andreas Blass in Journal of Physics A, and a forthcoming little paper with Andreas Blass and Alexander Wolberg. Wolberg is a functional analyst, but Andreas Blass is a fellow logician. And so the question arises, what logic has to do with all that? The connection is that logicians are, or at least used to be, much interested in foundations. So here are some famous examples. A joke is that when John von Neumann died, about 20 people became #1 in their respective fields. So the idea of negative probabilities looks crazy. And it's no coincidence that it arose in quantum mechanics, because quantum mechanics itself is somewhat strange. Not everybody is fine with this idea. For example, Itamar Pitovsky wrote about cheap tricks such as negative probabilities or even complex probabilities values. It's absurd to talk about an urn containing -17 red balls or 3 to the I pi over 12 wooden balls. And indeed, standard interpretation of probabilities is based on frequencies, and it doesn't apply to negative probabilities. But here is a very interesting analogy. What are numbers? Traditionally, numbers were quantities, integer quantities, rational quantities, real quantities. Now, the quantity like this one makes no sense. So what are negative probabilities? This question has two aspects. One is very formal. Generalized Kolmogorov axiomatic probability theory to account for negative probabilities. That's simple, and we'll address this aspect shortly. A more challenging aspect is ontological, what reality or at least intuition is behind the negative probabilities. I have no idea. Some good people, notably Richard Feynman, looked into these ontological questions and wrote about it. But as far as I'm concerned, the question is wide open. So the question that attracted me is much more pragmatic. What are they for? Can we take advantage of them, even if we don't understand what they are? And this aspect, that we don't understand something, but nevertheless use it, it's not new. In mathematics, it appears not so rare. For example, in 19th century, so the complex numbers, the question was, what is this imaginary one? I'm not sure today we can answer this very convincingly. So there was a kind of apprehension. Should we use complex numbers or not? But what we discovered that sometimes it just simplifies your life. So for example, you have a cubic equations like that with real coefficients. And for some coefficient, choice of coefficients, now you know that you have real roots, but those roots cannot be expressed in real radicals. So by Cardano's formula, the roots are expressed as cubic roots of complex numbers. This was quite a big issue. Those cases were called irreducible. So negative probabilities have proved to be useful as well, most importantly in quantum tomography. Now, preparing our paper on negative probabilities, we surveyed the literature and found that negative probabilities are presumably used in biology, decision theory, finance, information theory, and so on and so on, and so forth. I read a couple of those articles. None of them was very convincing, but I didn't read them all. What I can tell that in quantum computing, in quantum theory, they are used quantum reality. In quantum applications of quantum physics, negative probabilities are used, and we'll come closer to these applications later in the talk. Okay, models. So, being a logician, I want to formalize. So what are signed probabilities? So the definition seems to be quite obvious. Signed probability distribution on a measurable space is a real valued, countably additive function on a measurable space, such that the total probability is 1. There is this interesting remark. We actually didn't find this or any other definition in the literature. People just say that you need to weaken Kolmogorov axiom so that to allow the negative probabilities, but this seems to be the most obvious way to do it. So Kolmogorov was using fresh at the time measure theory to axiomatize probabilities, and measure theory helps us here as well. In physics, so mathematicians when speak about mathematicians speak about signed measures. Physicists speak about quasi-probabilities. I don't think they speak about quasi-measures, but probabilities which allow with negative values with passively negative values called quasi-probability distributions or simply quasi-probabilities. Countable additivity, of course, is standard law. The question is whether the law makes sense when probabilities are negative. A priori, the sum on the right may depend on the order of events, but actually it doesn't. By the way, I don't mind to be interrupted at any point, not necessarily to wait to the end if there is any question. So, laws of sign probabilities, what can be said about that? Many standard definitions and laws survive. So, for example, the expectation works as usual. If independent variables, if random variables are independent, then again, expectations work as usual. Deviations, standard deviation, the formula for standard deviation remains valid, but one should be careful. So some laws fail. So, for example, an event, probability of event may be bigger than 1. If event is of probability 0, it does not mean that every point inside is of probability 0. Or if you have two random variables, x and y dominates x at every point, it doesn't mean that expectation of x is dominated by the expectation of y. Here is a kind of simplest example that occurred to me when I was preparing this talk. Okay, and forward. So this is a fake quantum scenario. It looks like quantum, but I don't know whether it can be really realized as a quantum scenario, but it's so simple that it's convenient to use as a running scenario to illustrate things. So imagine the machine which keeps producing boxes with 2 bits, left bit and right bit. And there are 3 tests. You can look through the left window and observe the left bit. You can look through the right window and observe the right bit. Or you can test whether the bits are equal. And as you perform those tests, you find that invariably L equal 1, the left bit equal 1, right bit equal 1, but the bits are different. So in real quantum scenarios are very similar, but a little bit more involved. I just want to mention that in social, it's very easy to imagine that kind of scenario. There are 2 parties, whether husband and wife, or two states which don't like each other. You look from one point of view, you see their truth. You look from another point of view, you see the other truth. And of course, the 2 truths don't coincide. Okay, here is one of our first key definition. We create an observation space. What is an observation space? You have a non-empty set with a bunch of probability distribution, non-negative probability distribution, subject to the coherence constraint. So if some events occurred in the domain of 2 of these probability distributions, that they assign the same value. So observation space it's abstracted from typical examples in the literature. We'll look at one a bit later. So we say that an event is observable if it is in the domain of one of these probability distributions.
Sorry,
And
what is the
Yes?
sorry, what is the domain of the probability distribution?
Oh, just non-empty set, anything.
So is support, is it equal to the same as support?
Oh, no, the domains of different probability distributions may be distinct. They don't have to cover the whole omega.
Okay, okay, thank you.
And different events are co-observable if they belong to the same, to the domain of the same probability distribution. Intuitively, you make tests, and certain things you can test, and then you can see, or actually we'll see an example right away. Piponi's observation space. So in this observation space, the omega is pairs of bits. So there are 4 elements, 0, 0, 0, 1, 1, 0, and 1, 1. And there are 3 probability distributions corresponding to the 3 tests. So the domains correspond to those tests. So for example, looking to the left window, we know what do you see. You see, either you see that's what you really see. So always you have 1 on the left and something on the right. Okay, that's what you observe. Now, this kind of the complementary event never happens, but you observe that it doesn't happen. Okay, so looking to the right window, again, that's what you always observe, this event, and this is his complement. So this probability distribution corresponding to the left window is domain is generated by these 2 events. Okay, and so on. Notice that none of the sample points is observable. None. You always observe pairs. So if there are questions here, it's kind of trivial example, but nevertheless it shows how observation space works.
Negative probabilities never observed.
Go ahead.
It's true that negative probabilities in this model are not observed.
Professor Volovich, can you ask in Russian?
Это верно, что отрицательные вероятности не наблюдаемы.
Да. When you perform these 3 tests, there are no negative probabilities. They all non-negative.
Mm-hmm.
This is given. Okay, now we come to something more interesting. The question is there a probability distribution on the whole omega which is consistent with all given non-negative probability distributions? We call it a grounding. This is our key notion. So the question is there one explanation to all those tests? So presumably the reality, what happens in real world. So here's the definition of the grounding. So let's consider this Piponi's case. We have, let's see, first of all the probabilities, total probabilities should be 1. Probability of seeing 1 in the left window is 1. Probability seeing 0 in the left window is 0. Okay, similarly for the second test and similarly for the last test. So what happens, we have a system of linear equations. We solve them, and we get a unique solution. And the unique solution is this at the end. The probability of 0, 0 is -1/2, but all the probabilities of all other sample points are exactly 1/2. So there is the unique grounding. And so if there is one, whether you call it reality but mathematically one unique probability distribution which explains everything, it has to have this negative value. So the grounding problem arises. Is there a grounding for a given space? Is there a non-negative grounding? Is the grounding unique? Can you describe it in general? And turns out that a wide variety, as far as we could see, all examples that we knew of use of negative probabilities can be posed in this form. Professor Volovich opened my eyes for another class of examples which I didn't know, and he also hinted that it seems that the situation is similar. So I'm studying this gauge-related examples, but it takes a while. It takes a while. So a multi-test experiment over a Hilbert space is a particular state and a bunch of observables. So intuitively, you have laboratory examples, you produce the same state, and you perform one of tests. So for a while, we'll speak about finite dimensional examples. Now, for people who started physics long ago, that may seem too narrow, but people who work in quantum computing, the whole quantum computing is in finite dimensional spaces. It's a kind of glorified linear algebra. It's a little bit involved definition for a talk, but let me see. I will say that observation space models a multi-test experiment if there is an assignment of events to every eigenspace. So you perform a test, and as a result of the test, you observe one of the eigenvalues of your observable, say R. And for this R, there is maximal eigenvalue eigenspace, and this eigenspace is represented by some event in our observation space. And we require we impose natural conditions that these different events partition the whole space. So if you perform an experiment and you observe exactly one eigenvalue, therefore that explains this partition. And correctness that the probability of this event is the probability of observing R when you measure observable A. So these are two natural conditions. These are not the only natural conditions. If you have commuting observables, you may naturally require this one. we don't for a while, and in a moment you'll see. I'll explain why. So we have this modeling theorem. So every multi-test experiment is modeled by some observation space. So this somehow explains that our attempts to formalize multi-test experiments as observation spaces have been successful. So in the paper, we illustrate this theorem in a number of examples. Here I'll have just one example, which not most difficult, not most involved, but related to Feynman. So Feynman's experiment. So Feynman considers in mathematical terms a qubit in some state psi. Okay. You can think about photon or whatever materialization of qubit you like. And you observe one of two Pauli operators, Z or X. There's something strange in physics. When there are three Pauli operators, they are X, Y, Z. When there are two, they're always ZX. So I'll follow the way Feynman wrote it. Pauli operators, any of them, have eigenvalues plus minus 1. And so we have two observables. So our observation space is this. So there are just 4 points, plus, plus, you have plus 1, Z, observed Z, and so plus 1, observed X, and so plus 1, and so on. When you perform Z, you don't observe X, only the value of Z. So it's somewhat similar to, in a sense, even simpler than Piponia's experiment, except in some quantum mechanical real operators. So the domains are generated naturally, but as written. So Feynman didn't use the word grounding problem, but essentially he tried to solve it, and he found a solution. So following Feynman, instead of P at point plus plus, I write phi, little shorter, phi plus plus, f sub plus plus, f plus minus. So he wrote natural equations and found interesting solution. Here is his solution. So Y is the third Pauli operator. So the interesting part of this solution is that it's kind of symmetric. All the Pauli operators appear in kind of symmetric form. The solution has negative probabilities. Now, he never said what exactly he wants, so it's hard to argue. He says that he didn't find what he wanted, but I don't know what was he looking for. So we found a general solution, just a routine linear algebra. And turns out the general solution has one real parameter. And there is a region in the values of this real parameter, such that if you are within this region, there's always, so this region may be 1 point, depending on the state. Recall that everything depends on the state. I should say, for those who don't know what this Z in this strange parenthesis is the expectation of z. So these are just numbers in a given state. So the whole thing depends on the state. But there is always at least one point, but typically a whole interval of values which give you purely non-negative solution. So here's a kind of general solution in this particular case. We also analyzed a 3-test experiment. There were many more equations. It's still linear algebra, but much harder to do by hand. So we did our best. And in the paper, there are a number of other examples of that sort. But now we go to something else. Yes, there is one limitation.
Excuse me.
Yes, go
Can I
ahead.
ask you, do you that in experiments with Pauli matrices, you can get negative probability?
So if a real parameter outside of this interval and the one value that was chosen by Feynman is always outside, then you get negative probabilities. So you get positive probabilities if and only if this real parameter is within this interval, little m, between little m and big M. Professor Volodych, did I answer your question?
It sounds strange for me, because in this simple experiment with Hermitian Pauli matrices, we have the von Neumann postulate axioms for this quantum system. At always there is only positive probabilities.
Yes, we also were surprised.
May I say, I am not surprised because you are speaking about incompatible observables. And when you try to fit results of measurement or expectations of incompatible quantum observables into one probabilistic scheme, you get this negative quasi-probability, like with Wigner function in continuous case. But you elaborated nice, I think most elementary example of this phenomenon. And
Right.
also it is interesting that sometimes you still get non-negative.
Yes.
Yeah. I am most surprised by this.
Yes, I completely agree. That's precisely what it. So in the 3-test experiment, there is also a region of non-negative groundings. So now let me say about one limitation, and it is related to so-called contextuality. So it's a strange issue, this contextuality. It was, the term was coined by philosophers, and when you read philosophers, you get headache in no time, and you don't know exactly what they're talking about. At least philosophers who wrote about this. So, for example, even though they all speak about contextuality, there seems to be no definition that everybody agrees. So we coined our own definition along the lines what we think is contextuality. But we checked that all the standard examples of contextuality work as intended. So we say this set of observables is contextual if every function that assigns an eigenvalue to each observable, then what happens is there are, for every such function, there are commuting observables such that their values are not simultaneous eigenvalues of these commuting observables. So if you have commuting observables, they have simultaneous eigenvalues. But contextuality, what philosophers found very interesting, which is actually interesting, that in certain cases, you do experiments and you observe this contextuality phenomenon. And it turns out that none of the contextual, if you have this, if you have multi-tests which exhibits contextuality, then it cannot be monotonically modeled by an observation space. So we actually proved this theorem because of reviewer. One of our reviewers was super interested in contextuality, and he was interested to know more about that. And but turns out that contextuality is a real problem in this area. Okay, now to the beginning, as Professor Kholeva noticed, Wigner's experiment. Okay, in the beginning, this Hebrew word is the first word in the Hebrew Bible. Now we allow infinite dimensional Hilbert spaces. So our hero is Eugen Wigner. So what's the problem? The uncertainty principle limits the precision of knowing position and momentum of a particle simultaneously. Physicists may say of limits positions, momentum having simultaneous values. Now, here's a little bit more cautious formulation and knowing such values. So quantum mechanics determines the probability distributions of position x, of momentum p, but their joint distribution makes no physical sense. Yet, in 1932, in a very famous paper, Eugen Wigner exhibited such a joint distribution. So Wigner, also Nobel Prize winner and famous guy, but he's very different from Feynman. He doesn't think aloud. I have no idea where he's coming from. He just mentions there in a footnote that he and Leo Szilard looked at something and came across this. The only remark which is worth mentioning is this: some of the values of negative of Eugen this probability distribution happens to be quasi-probability distribution, and some of its values were negative. But of course, writes Wigner, this must not hinder the use of it in calculations as an auxiliary function, which obeys many relations we would expect from such a probability. And he was right. This is a good, practical, pragmatic view. Okay. I wanted to give a little primer for people who are not so versed in quantum theory as Professors Kholeva and Volovich. So position. For simplicity, we consider one particle particle moving in one direction, then the state space is the Hilbert space called L2 of square integrable functions where the linear product is given by this Lebesgue integral. Now, if you look for the first time, you say, why? What kind of, why a state should be a function with complex values on real numbers? Because the particle is also a wave. And experimentally, you find out that you can find probability density of position. And okay, that is the root of the explanation. The position observable is given by this operator. So we'll write P sub capital X for the probability distribution with this density function. Let me put a physicist's hat on. So what's the problem? Let me go back for a second. Notice that the density function exists in every state. And so the probability distribution P sub capital X is well defined in every state. But X itself may not be square integrable. So the capital X itself may not be, capital X applied to psi, to the state, may not be a legitimate state. So when you work with physicists, you find interesting phenomena, just don't worry about it. Momentum, it's a little bit more complicated, but it's essentially the same story if you use Fourier transform. So a proper explanation would take me far and take time, but basic explanation is in the called de Broglie relation. So the momentum and the wavelengths are connected with this so-called de Broglie relationship. Okay, the end of primer. So Wigner's quasi-distribution is given by the formula which Wigner wrote in that 1932 paper. And he claimed that, let's fix a state. So the dependence on the state will be implicit. So as you see, Wigner's quasi-distribution depends on state. So in each state, you have kind of quasi-distribution, but it's always defined. And he claimed that P sub X and P sub P are correct marginal distribution of his quasi-distribution, and that's true. So in our terms, Wigner's quasi-distribution is a grounding for this simple observation space. Now, here is the proper role. This is the main technical result. Maybe I should say a few words about history. We had a form of this result in 2014, just when I started to work on quantum computing. Knew very little, was almost perfectly ignoramus and tried to learn. And I dragged my collaborator Andreas Glass, with whom we have by now, I don't know, maybe 60, 70 more joint papers. He was physicist in his bachelor's degree. And so we looked into this problem. So we formulated this theorem and sketched the proof, actually not sketched, actually we wrote a kind of tutorial, not very ambitious. I have a column in one of European journals, the Bulletin of European Society of Theoretical Computer Science. So we wrote a column there on this and explained things nicely, but not all of it. So in a sense, it was a kind of sketch. Then we discovered, actually the last moment, we were able to give credit to a husband and wife team in France, Bertrand et Bertrand, who gave a physical sketch of this result. So the result, they noticed this thing first. Their sketch is definitely not mathematical. So here we prove it in mathematical terms that Wigner's quasi-probability is a unique grounding if you consider not only marginal distribution for for position and momentum, but also for all their linear combinations. Okay, putting back mathematical hat, the uniqueness claim happens to be a special case of a purely measure theoretic fact. We didn't find this fact in books, even not in Bogachev's measure theory, which is probably the most informative book on the subject. So we had to prove it on our own. The proof of correctness is more involved. I can't go into it, but let me address a simple question. So does the theorem apply to all states? As far as physicists is concerned, it's not so important question, because in physics, now if you measure, there is certain precision. So if you have a collection of nice states, which is everywhere dense, you're good. But mathematically, it's still interesting, and the answer is positive. As I mentioned before, the probability P sub capital X is defined in every state, even though X applied to this state may not be a legitimate state. The same situation happens to with momentum, and took us a while, and that's where our functional analysis expert comes. Turns out that any observable Z of that form is a unitary conjugate of momentum. And so the density function for any linear combination is defined everywhere. Wigner's function is defined everywhere. So you can prove that this theorem holds in every single state, whether it has mathematical physical sense or not. It seems to have a good mathematical sense. That's it. Thank you.
Thank you very much, Professor Gurevich, for the very interesting and stimulating talk. Questions, please.
Hello?
Yes, please.
We are thinking about questions.
Okay.
Okay, comments.
Do you have examples of, so to say, real usefulness of quasi-probability distribution? Of course, thank you very much for your nice talk, and I like especially the first discrete part. It was new for me.
Yes, we do.
Yes, but do you know instances where using this quasi-probability distribution is really useful? I know some people who use quasi-probability distributions in studying Bell inequalities, for example. Also, I think also our friend Andrei Hrennikov was interested in negative probabilities, and maybe you have some other instances where this introducing negative probabilities is useful in some calculations, as Wigner suggested. And in fact, he gave the most important example where it is the case.
Yes. So I agree that Wigner gives the most important example. I do not know any use of negative probabilities for theoretical purposes. What I do know secondhand, that negative probabilities, Wigner's distribution and similar things are used extensively in quantum tomography for real. Now, how do I know that? So I read a couple of papers, which wasn't easy for me. For somebody educated in algebra and then logic, plenty of engineering, but physics is altogether a new subject. But I also spoke to people, at the time I was at Microsoft Research, and we had a very strong group. So I spoke to a couple of people who were mostly none of them was personally involved in optic tomography used in quantum physics, but all of them assured me that the papers that I read are real, that it's used for real. So essentially, tomography is like MRI, or like what you do with the human body. You do similar things here with physical body. And when you do tomography, you essentially look at plane marginal distributions over the planes. And they're all non-negative, so they make good sense. But when you want to integrate the whole thing, negative probabilities arise here and there, typically in small regions. But in other regions, you can use it. And so that's how it works. So they used for their computations cautiously. And I think a couple of papers that I read left me with an impression that a good theorist, which is willing to dirty his hands and willing to go to this field and work with experimenters will probably be very useful there.
Thank you.
Okay, more questions, please.
May I ask a question? Thank you also for the very interesting talk. My question is about a comparison of your discrete part with the discrete Wigner functions. So it's very interesting that you say that a Wigner function is a grounding for the continuous case initially presented for the discrete in the discrete version. But there is some works about discrete Wigner functions. I'm not very familiar with these works, but I heard about them. So could you compare your approach with grounding in the discrete case and the discrete Wigner functions?
I think I'm exactly where you are. I heard about Wigner's discrete function. I don't know anything about it. Maybe I should explain a word so not to pretend to be who I am not. So I started at Chelyabinsk Polytechnic, when transferred to Ural University, which is a nice university. It wasn't MGU, it wasn't LGU. And then I read a book by Klini called Introduction to Mathematics, and I became so much interested in mathematics, but I didn't know what to do. So I started to do some logic. Eventually, I joined Maltsev's Algebra and Logic seminar and solved some problems. So when in 1973, I came to Israel, they gave me credit for solving problems. I got a good position, but discovered I'm completely ignorant in modern logic, set theory, enforcing. So it took me a decade to catch up on that. And then I continued when I was still in Urals. I worked in applications in transportation industry just to get some money on the side, but developed a taste to them, to applications. And then I wanted to move to computer science, and that's why I went to the United States, intending to return back to Israel, but never did. And so United States became theoretical computer scientist, started to move, invented something so-called abstract state machines. Microsoft became interested, invited me to start a group. And suddenly this mathematician was supposed to build something in Microsoft. And then I worked with engineers and eventually learned this engineering culture. And after many years, we created a new group in quantum computing. And one of these guys, actually a Russian guy, came to me and asked about one of my group theoretic papers because he wanted to use it. And I started to attend their seminars, and my mathematical interest returned. So as far as quantum physics is concerned, I'm a newbie. In 1914, I just started. But there it was, we built something. The group was called Architecture and Computing. So there were people who were actually building something so you could learn. By now, I retired from Microsoft, first from Michigan, then from Microsoft. And now I don't have any access to working physicists. So that explains why I didn't rush to talk to experimentals to work in quantum tomography. Sorry for this super long answer to simple question.
Thank you very much. Very interesting.
More questions, please, or comments? Let me ask you about Feynman. You mentioned,
About?
you quoted Richard Feynman's text that quantum mechanics is involved, deals with negative probabilities. Can you comment more about this? What he meant? Maybe a Wigner distribution?
No. So he was the first to think about quantum computing. The other one was Yuri
Manin.
Yes, yeah, thank you. Feynman had a very reasonable idea. You want to model quantum reality. How do you model quantum reality? How do you model things? Find some another reality which is described by the same equations, by the same math. That's the easiest thing to model. Study the other reality, since they described by the same mathematics, you study the same thing. So the bulk of his book, so here is this, is about building quantum using quantum computing to study quantum phenomena. And he used cellular automata. Many years later, more mathematically oriented people came to the field, and instead of cellular automata, they used Turing machines, which is, I think it's a silly idea. Turing machine is so strange for quantum things because it's so deterministic. So even if you make transitions, quantum randomizing quantum, it's still just in one place. Everything goes. Everything else is sort of passive and waiting. But that's how later development went. But he saw immediately reality as it should. Now, as he was describing this mathematical models of what quantum computers should do, and that is where he discovered negative probabilities. Unfortunately, he doesn't say too much about that. So the maximum what is there's his talk, not in this book, a separate talk he gave. One of the colleagues had some anniversary. He gave a talk called Negative Probabilities, published separately. And there he speaks a little more, but what that talk is essentially kind of foundational logical talk. He wants to develop an intuition behind negative probabilities. So he compares them to negative numbers, and he never says where exactly negative probabilities arose, as far as I see. Now, I didn't investigate, I'm not a historian of Richard Feynman, and so in various places, as I said, he likes to, my impression, I never met him, my impression is that he likes to speak loudly, to think aloud, and so probably here and there are his thoughts in various papers, but that's all that I can say.
Okay, thank you. More questions, please. I would like to add to the list of people, maybe great people, who discussed negative probability, also Werner Heisenberg and Pauli. They were involved in negative probability discussion to struggle with ultraviolet divergences in quantum field theory. But it was long ago. As another remark, let me say that basically it's a question of terminology. We could say negative probability, or instead we could say quasi-probability.
Yes.
Yeah.
Also, Dirac wrote in about 1942. So later, many people looked into it.
Mm-hmm. Okay, some more questions?